In lecture 31, we're going to talk about the polar form of the complex number, thinking of the complex plane as a rectangular coordinate system that can then be converted into polar coordinates. We can then think of or rewrite our complex numbers in their polar form. And then once we have their polar form, there is a theorem that allows us to do things like the square roots and the powers of complex numbers, which we would not be able to do without, or at least not easily, without their polar form. So we're going to convert between the forms. We're going to find products and quotients when they're in polar form, which actually turns out to be much easier than even the FOIL or the distribution method. And then DeMoivre's formula is that formula that allows us to do things like powers and roots of complex numbers. And then now that we can find roots, we are going to think of the fact that turns out there are several, well, if you have a cube root, there are actually 3 different values in the complex plane that would be the cube root of any number. You can find 4 different fourth roots and 5 different fifth roots and 6 different sixth roots and so on. To begin with, let's start talking about the polar form of the complex number. Note, a complex number written as z is equal to x plus yi is said to be in rectangular form. Now, if r is greater than or equal to 0, and theta is some angle between 0 and 2 pi, or 0 and 360 degrees, depending on your mode that you are in, the complex number z is equal to x plus yi can be written in a polar form. And we can do so by recalling that if we find the r and the theta, right, that are the polar forms for x comma y, then x is related to r and theta by the formula x is equal to r cosine theta, and y is r sine of theta. So we can replace x with r cosine theta and y with r sine theta. And since these both have an r in it, we can factor the r out and rewrite this as r cosine theta, r plus I sine theta. Remember this I from the imaginary unit that is in the complex number. And as we defined in the last lecture, r is called the magnitude or modulus of z, which we can rewrite as this absolute value format. We don't actually say it as the absolute value of z, we say the modulus of z when we're talking about complex numbers. And then theta is called the argument of z. Converting between polar and rectangular form is exactly the same as converting between polar and rectangular coordinates. So, for example, if we are given a number in rectangular form, we would want to find the r and the theta, so we can rewrite this as r times cosine of theta plus I sine of theta. So we just need to know where are we in the coordinate system, and then find the r and the theta that goes with that coordinate. This is the point in the complex plane. If this is the real axis and this is the imaginary axis, this is the point square root of 3 comma negative 1. All right, so square root of 3 is about 1.7, so right here, and negative 1 is right down here, so we're looking at a point right here. Okay, where this side right here is square root of 3, and this side right here is negative 1. So your r, which is actually your magnitude of z, is the square root of x squared plus y squared, or the square root of square root of 3 squared plus a negative 1 squared, which is the square root of 3 plus 1, or the square root of 4, which is 2. All right, to figure out this theta right here, remember that we first find theta sub r. Theta sub r is the inverse tangent of the absolute value of y over x, so that's negative 1 over square root of 3, which is the tangent inverse of square root of 3 over 3, absolute value making it positive. We look it up on our table or whatever, we find that that is actually 30 degrees, which means theta is a 360 degrees minus 30, since we're in quadrant 4. means 330 degrees. Now, it is most common in this context and in this chapter to think of theta, when we're talking about polar forms of complex numbers, just to write it in their degree format. So the final answer here would be that z is 2 times cosine of 330 degrees plus I sine of 330 degrees. And just like converting from polar to rectangular is a very easy thing to do, you can do that very easily with complex numbers as well. If your complex number is written in this form, 2 cosine 30 degrees plus I sine 30 degrees, that's the same thing as 2 cosine of 30 degrees plus I times a 2 sine of 30 degrees. Cosine of 30, remember, is just square root of 3 over 2. So you have 2 times the square root of 3 over 2 plus I times 2 times 1/2, because the sine of 30 is 1/2. That gives you a square root of 3, because the 2's cancel here and the 2's cancel here, so you have just plus I. Square root of 3 plus I is your rectangular form, or a plus bi form of z. So why do we consider polar form at all? Why not just work with rectangular form, since we are able to add, subtract, multiply, and divide? Well, it turns out that it's actually even much, much simpler to multiply and divide complex numbers. I mean, you'll recall how much of a tedious process it is to just divide complex numbers when they're in rectangular form by having to multiply through by the conjugate of the denominator. It's not that bad, but it's still a whole lot more work than what you're about to see. Look at this theorem. It says if I have a number, complex number, z1, which is r1 times cosine theta 1 plus I sine of theta 1. So it's a complex number in polar form. And let's correct the typo here. This should say z2, r2, theta 2, and theta 2 here. So you got a second complex number in polar form. So it's got a different radius or modulus, and it's got a different theta 2, which is a different argument. And you multiply those two things together with some simplification and an application of a trigonometric identity, you've got the following formula that falls right out. The product of a complex number times a complex number is a new complex number in polar form, where the modulus is the product of the two moduli of your complex number. So it's r1 times r2, and then your new argument is the sum of your two previous arguments. Again, let me say that again. Your product of two complex numbers means just multiply the two moduli together and then add your arguments together. And you've got now this formula right here, which gives you the product. So you don't even have to really do any multiplication. You don't have to worry about I squareds. All you got to do is multiply their r's and add their thetas, and that's your new complex number. To divide is actually just as easy. As long as z2 is not a zero complex number, you've got z1 divided by z2 is r1 divided by r2 times, and then you subtract the two arguments. And you got to be careful, as long as if you subtract these, if they get negative, you just add 360 degrees to it to get it to be positive again. So look at these two. I got z is 3 cosine of 20 plus I sine 20, and w is 5 cosine of 100 plus I sine of 100. So up here my r1 is 3 and my theta 1 is 20 degrees. And over here my r2 is 5 and my theta 2 is 100 degrees. Which means to multiply this together, I'm just going to take r1 times r2 cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Multiply your moduluses, or your moduli, that's 3 times 5, and then add your arguments inside. Theta 1 plus theta 2 is 20 plus 100 plus I sine of 20 plus 100, which means I get 15 cosine of 120 degrees plus I sine of 120 degrees. just like that. That's it. That's all there is to do it. In fact, I don't even have to write down. It's not even nearly as long as it took me to write it down. If I did R1 over R2 to divide, I mean, Z over W is going to be R1 over R2. That's times, come on, erase. Cosine of 20 minus 100 plus I sine of 20 minus 100, which is 3/5 cosine of negative 80 plus I sine of negative 80. And that shouldn't be there. And since negative 80 is not between 0 and 2 pi or 0 and 360, we're going to rewrite that by just adding 360 degrees. Since that's the equivalent sine and cosine, this becomes 3/5 cosine of 280 plus I sine of 280. And that is your polar form of that complex number, which is the quotient of those two. No conjugates. All you got to do is divide the moduli and subtract the arguments. DeMoivre's theorem is an extension of the previous theorem based on the fact that if you multiply two complex numbers together, you multiply their moduluses or magnitudes together, their r's, and you add their arguments. So, in order to raise a complex number to a power, that is, if you're going to multiply it times itself a certain number of times, you can apply that same concept, and you're just going to multiply that its modulus times itself that many times, that r, and then you're going to add the argument to itself that many times. And if you add something to itself n number of times, you get n times that value. So z to the n, if z is r cosine plus I sine, or r times the product, or the sum, cosine of theta plus I sine of theta, so you got a complex number in polar form, to raise it to a power, to raise it to the nth power, is to raise its modulus or magnitude to the nth power, and its new argument becomes n times the original argument. As long as n greater than or equal to 1 is a positive integer. And it's inductively true. You can just see it's a direct application of that previous theorem. So think about it. If I want to take 2 cosine of 20 plus I sine of 20 and apply DeMoivre's theorem, this is simply going to be 2 to the third times cosine of 3 times 20 degrees plus I sine of 3 times 20 degrees. Because you just take the cube and you cube the 2, and then you're going to take these both times 3 to get the new argument. So this becomes 8 times cosine of 120 degrees plus I sine of 120 degrees, which is the polar form. If I do ask you to go ahead and convert it to rectangular form, just recall all you got to do is remember to take the cosine and the sine. So what is cosine of 120 degrees? It is a negative 1/2, and I sine, so of 120 would be I times square root of 3 over 2. If you multiply the 8 times each of those, you get a negative 4 plus a 4i square roots of 3. Because 8 times square root of 3 over 2 is 4 square roots of 3, and we write that as 4i square roots of 3. And there you go. That's the rectangular form. And think about how simple that is. If you had to multiply something times itself twice, you raise something to the third power, well, that's 2 multiplication problems. You would have had to do FOIL twice if the problem was originally in rectangular form. So this polar form saves you a ton of work. Like this one, this should be not I plus I. This problem, let's write that as 1 plus I to the 5th. Okay, that's a typo right there. That's 1 plus I to the 5th. Now, the long way would be to do 1 plus I times 1 plus I times 1 plus I times 1 plus I times 1 plus I. You'd have to FOIL these, get an answer, and then FOIL these, and then FOIL these, and then FOIL the result. An enormous amount of work to be able to get to this fifth power. But I can erase all this, and if I simply convert 1 plus I to polar form, I can then apply DeMoivre's theorem. So let's do that. What is 1 plus I in polar form? Well, 1 plus I is the real part is 1 and the imaginary part is 1, so it's over 1 and up 1. We're right here. Okay, so the modulus of z, which is the r, is the square root of 1 squared plus 1 squared, or the square root of 2. Theta would be, well, it's this right here. If that's theta sub r, it's the tangent inverse of 1 over 1, or the tangent inverse of, of positive 1, which is 45 degrees. And so theta sub r is that which is also theta, since we're in quadrant 1. Right? Theta and r, the reference angle is the same as the angle itself. So z is equal to 1 plus I is the same thing as the square root of 2 times cosine of 45 degrees plus I sine of 45 degrees. So z to the fifth would be a square root of 2 to the fifth power times cosine of 5 times 45 plus I sine of 5 times 45, which is square root of 2 times square root of 2 is, these two become a 2, these two become a 2, so you actually end up with 4 square roots of 2 times cosine 5 times 45 is 225 degrees plus I sine of 225 degrees. And then let's rewrite the answer back in rectangular form. So that's 4 square roots of 2 times cosine of 225 is a negative square root of 2 over 2, because 225 is in the third quadrant and cosine is negative there, plus actually this is going to be also minus, so you get minus I times square root of 2 over 2, because sine of 225 is negative root 2 over 2. And if you distribute this, 4 and 2, both the 2 divide out. Square root of 2 times square root of 2 is 2. 2 times 2 is 4, so I get a negative 4 minus, and I get the same thing here again, so it's minus 4i. That is 1 plus I raised to the fifth power. Now there's some work to be done in there, but it is still a whole lot simpler than having to multiply out a binomial 5 times. We can also turn DeMoivre's theorem kind of on its head, basically thinking of it in reverse. So let's say instead of knowing the complex number we want to raise to a power, let's say we know the answer and we want to find out what do I have to raise to a power to get to this number. That's the concept of a root. So let's say I knew z to the fifth was some complex number. How do I find what z was? That's finding the fifth root of a complex number. Well, since DeMoivre's theorem says to find a complex power, all I have to do is raise the modulus to a power and multiply the argument by that power. To find the root is the reverse of both those questions. I will want to find the root, that is the number that I have to raise it to a certain power to get, that is the root of r, and then instead of multiplying, I'm going to divide. I'm going to divide by n. So recall that the nth root of a number, x, is y that satisfies this equation, and we write it as the nth root. Now if w is a complex number, any complex number z, and the key word here is any, because there's going to be actually multiple ones of these, z to the n equals w is called the complex nth root of w. If n is 2, we call it a complex square root. If it's n is equal to 3, we call it a cube root, but after that it's fourth root, fifth root, and so on. Another thing that turns out to be true, and you'll actually see why as we work a couple of examples, every number w, there are actually exactly 2 complex square roots, right? If n is equal to 2, there's 2 complex square roots. If n is equal to 3, there are actually 3 complex, in this case, cube roots. There are 4 complex fourth roots, and so forth. How do we find them? Well, the first one is easy, and the rest of them, that is the first one of the 2 for square roots, the first one of the 3 for cube roots, the first one of the 4 for cube roots, are actually very, very simple, just like I was explaining before. You take the root of the modulus and you divide the argument by the root. So if w is r cosine of theta naught plus I sine of theta naught, and n is the index of the root, then to find your complex roots, and there will be, I'm using subscript notation here, for each k, 0 up to n minus 1, you just take the nth root of r, which is again, the n you're trying to find the root for. N is 2 for square roots and so on. And you find theta naught divided by n to get the new argument. But that's only one of the roots. To get the rest, you take one complete rotation and divide it by n, and you keep adding that number to get the other arguments for all the other roots. So let's walk through that with an example. So you can find, in this case, we're asked to find cube roots. So how many are there? The answer is there's going to be 3 of them. So how do I find those 3? Well, first convert to polar, because that's what w would have to be in our little explanation above. Convert to polar. So in this case, negative 1 comma square root of 3 would be in the second quadrant. Negative 1 square root of 3 is about 1.7. So up here, negative 1 square root of 3. So we're in quadrant 2. Your r is going to be the square root of negative 1 squared plus square root of 3 squared, which is square root of 1 plus 3, or square root of 4, or 2. So r is 2. Your theta sub r, your reference angle, which is this theta here, and I'm trying to find the theta over here. Theta sub r is going to be tangent inverse of y over x, so negative square root of 3, which turns out to be a 60-degree angle, which means that theta is 180 minus 60, or 120 degrees. Why is it 180? Because 180 is the straight angle, and I subtract theta r because I'm in quadrant 2. So then my complex number, which I'll call w, if I call this here w, is in polar form 2 times cosine of 120 plus I sine of 120. All right, so here's what we do to figure out the 3 complex roots. We're going to do this for, I'm really just using this formula right here. I'm going to highlight it. This formula is all I need to find the complex roots. Always out front, so for z1 will be the cube root of 2 times cosine of 120 divided by 3, right? Because n is equal to 3 in this case. And then plus 360 over 3 times k, which is times a 0. Right? 360 over n plus, or times k. Sorry, this should be z0. Because I start with k equals 0. So z0, k is 0. I'll do one for k equals 1 and k equals 2. That will give me 3 different answers here. Plus I sine of 120 over 3 plus 360 over 3 times 0. So that gives me the cube root of 2. I wrote that backwards. Let's try that one more time. It gives me the cube root of 2. This is cosine of 40 plus 0. There's my first cube root. Now my second one, which I'll move this down a little bit, so k equals 1. Z1 would be still the cube root of 2, cosine of 120 over 3 plus 360 over 3 times 1, plus I sine of 120 over 3 plus 360 over 3 times 1. So that gives me a cube root of 2. This is 40 here. 360 divided by 3 is 120. So 40 plus 120 times 1 is cosine of 160 plus I sine of 160. There's the second cube root. And the third one, z for k equals 2, would be cube root of 2 cosine of 120 over 3 plus 360 over 3 times now 2 plus I sine of 120 over 3 plus 360 over 3 times 2. So this is again 40. This is 120 times 2. What you're really doing is you just keep adding 120 as long as you can and before you pass a full 360 degrees. So in this case, that leaves me with cube root of 2 cosine of 160 plus another 120 is 280, or you can think of this as 40 plus a 240, because it's 120 times 2. 40 plus 120 times 2, or 40 plus 240, is 280. I'm still inside of 360 degrees then. This right here is my third cube root. These three complex numbers, when you cube them, will give you negative 1 plus square root of 3 times I. That's how you find a complex root. Now let's think of this in terms of its geometric interpretation. The first answer that we got was the cube root of 2 times cosine of 40 degrees plus I sine of 40 degrees. So if you think of that in the complex plane, this is the real axis, this is the imaginary axis, so this is the complex plane. This distance here, that is the radius of the circle I've drawn, is the cube root of 2. This point right here corresponds to that complex number, because it has an angle of 40 degrees and a modulus of cube root of 2. Now what I did to get the second one was I added 120 to the argument. That's all I did. I added 1/3 of a whole rotation, 360 degrees divided by the index of the root, which was 3. To add that 120 degrees meant I went 1/3 of the way around the circle. All right, so this over here is the cube root of 2 cosine of 40 plus 120, or 160, plus I sine of 160. And then to get the third cube root, which is this point over here, I went another 120 degrees around again. I added 120 to this, or another 120 over here, which got me to cube root of 2 times cosine of 280 degrees plus I sine of 280. So the first point comes from just using DeMoivre's theorem in reverse, and the other two come from taking one full rotation and dividing it into pieces, where those pieces are, the number of pieces are the root index. So 1 piece, 2 piece, 3 piece. So there's the first complex cube root. The second one would be 1/3 of a rotation around. The next one is 1/3 of a rotation around. The last example I want to show you is one that will hopefully kind of expand your understanding of complex roots compared to roots that we talked about for the real number system. If I were to have given you a problem prior to this lecture and said, what is the 6th root of 1? You would probably tell me 1. You may have been ingenuitive enough to come up with -1, because you also take -1 to the 6th power. You get a positive 1. But in general, that's where we would stop. when we were talking about complex numbers, because those are all the complex numbers such that if I take it and raise it to the 6th power, I get 1, right? And same thing is true for -1. But according to what I said earlier, and I'm going to go ahead and scroll up and let you see it again, this statement right here would say that there are how many 6th roots of the number 1. Now, 1 doesn't seem like a complex number, but we've already said all real numbers are complex numbers. So yes, we can find the complex roots of 1. There should be 6 of them, and then according to what we just came up with, we only have 2 so far. How do we find the others? Well, we're going to use the formula we introduced right up here, highlighted in yellow, to find all 6 of them. Basically, you find the first one, and then you add 1/6 of a rotation to its argument 5 times to get the 5 other roots besides that first one. All right, so the easiest way to think of this is in terms of, think of it a complex number, right? This is 1 plus 0i. Convert to polar form. Polar form is pretty simple because you just got to remember where is 1 plus 0i on the complex plane. If this is the real axis, imaginary axis, we're over at 1 and up 0. Right, which means that r is 1. That's the distance. And then the angle is also 0 degrees. So this looks like that w, calling w1, is 1 times cosine of 0 degrees plus I sine of 0 degrees. So here's my r, and here's my theta. Now applying the theorem, or the yellow highlighted formula from above, I can do for k equals 0, k equals 1, k equals 2, and so on. I find that the 6th root, the first 6th root of this number w would be z sub 0, which is the 6th root of 1 times cosine of 0 over 6 plus 360 over 6 times 0, plus I sine of my argument over 6 plus a full rotation over 6 times my k, which is 0. So in this case, I get 1, right, times cosine of 0 plus I sine of 0, because this is 0, this is 60. 0 plus 60 times 0 is still 0. And then multiply those out. What is cosine of 0? Cosine of 0 is 1. Sine of 0 is 0. So I get 1 times 1, which is a 1. So z0 is 1, which happens to be my first complex root that I listed above. Now what happens if I do k is equal to 1? All right, let's try z1. So k equals 1 would be, again, the 6th root of 1, cosine of 0 over 6 plus 360 over 6 times 1, plus I sine of 0 over 6 plus 360 over 6 times 1, which is a 1 times cosine of 0 plus 60, so that's 60, plus I sine of 60. Now cosine of 60 is 1/2, and sine of 60 is square root of 3 over 2. So I get 1/2 plus square root of 3 over 2 times I. That number right there, complex number, is a 6th root of the number 1. If you multiplied it times itself 6 times, you would get 1. Kind of surprising, but it is in fact true. K equals 2. I'm going to start kind of shortcutting this a little bit because I begin to notice a pattern. This is the 6th root of 1. I'm going to be taking now 0 over 6 plus 360 over 6 times 2, which is going to give me a 120. I'm just going to keep adding 60 degrees each time. So that's 1 times the cosine of 120, which is a negative 1/2, plus the sine of 120, which is positive square root of 3 over 2, So that gives me a negative 1/2 plus square root of 3 over 2 times I. There is my next complex root, sixth root of the number 1. Z3, k equals 3, would be the sixth root of 1 times cosine of 180 plus I sine of 180, which would be, again, 1 times, I'm just going to skip the step of writing down the 1. Cosine of 180 is a negative 1, and sine of 180 is 0, so you get negative 1, which, by the way, was the second one we had come up with. Our fourth root that we've gotten so far of the answers was the one that we thought of earlier. To do the next two, which will be the last two, k equals 4, k equals 5, Z4 would be the sixth root of 1 cosine of, add another 60 to that, you get 240, plus I sine of 240 is negative 1/2 for cosine of 240 and a negative square root of 3 over 2 for sine, so it's times I. And then the last one, which would be Z5, is the sixth root of 1, add another 60, you get 300, plus I sine of 300. Cosine of 300 is a positive 1/2. And sine of 300 is a negative square root of 3 over 2. 1, 2, 3, 4, 5, 6 different numbers that if you raise them to the sixth power, you get 1. You can find the complex sixth roots of the number 1 simply by using this process. All right, and that's that. That's the end of lecture 31.